Right now, as you watch this video, your body is running through thousands of chemical reactions. Your cells are generating ATP to keep things functioning, your stomach is breaking down whatever you last ate, or whatever you're currently eating, and if you're watching this on a phone, that battery is driving electrochemical reactions to power every single pixel on your screen. We tend to talk about chemical reactions like they're simple, like they're nothing more than equations on a chalkboard. Reactants go in, products come out. But that's kind of like describing a symphony as sounds go in, music comes out. There's an enormous amount happening underneath the surface. So today, let's pull back the curtain on what's actually happening during a chemical reaction. Hello and welcome to the Chemist's Codex. My name is Peter, and I like to find stories in the things that catch my interest because I believe those stories can teach us more about ourselves. This video isn't so much a story, but chemical reactions are something every single one of us interacts with every day, and most explanations you might know stop at the equation. There's a surprising amount happening inside a reaction that a simple equation just doesn't capture. So let's go ahead and fix that. But before we get started, make sure you subscribe and hit that notification bell so you never miss when I upload a new video. Now that you've done that, let's get into some chemical reactions. Starting at the most foundational level, the 5 types of reactions you learn in a high school chemistry class. But before we even get to the types, there's a concept worth flagging that makes everything else click: balancing equations. When we write out a chemical reaction, we put reactants on the left and products on the right, with an arrow in the middle. And there's a rule we always have to honor: the law of conservation of mass. Atoms cannot appear or disappear during a reaction. They just rearrange themselves. Whatever atoms you start with on the left have to show up on the right in the same quantities. Balancing equations is simply the accounting that confirms we've honored that rule. Every example we're about to look at obeys it, so keep that in the back of your mind. Synthesis reactions are conceptually simple. Take 2 things, combine them, get one new thing. A plus B yields AB. A textbook example of a synthesis reaction is ammonia, combining nitrogen gas and hydrogen gas under extreme heat and pressure to produce NH3. Now, that might sound like a footnote in a chemistry lecture, but the industrial production of ammonia through this reaction, the Haber process, is arguably one of the most consequential chemical developments in human history. Ammonia is the foundation of synthetic fertilizer. Without it, estimates suggest we couldn't produce enough food to sustain roughly half the current global population. One synthesis reaction feeding billions of people. If you want to know more about this reaction and the complicated man who pioneered it, you can check out the video I did about Fritz Haber. There will be a link in the description. Another classic synthesis example is the reaction between sodium and chlorine. Pure sodium is a metal that reacts violently with water. Chlorine was used as a weapon in World War I. Combine them correctly and you get sodium chloride, otherwise known as table salt. Completely benign, biologically essential. The product shares nothing in common with either of its starting materials. Now, decomposition reactions are kind of like the opposite of synthesis. One compound breaks apart into 2 or more substances. C yields A plus B. A great example of decomposition is the electrolysis of water. Pass an electrical current through water and it splits into hydrogen gas and oxygen gas. You're using energy to pull apart something stable. Straightforward enough? But there's an even better example of a decomposition reaction that's an iconic chemistry demonstration: elephant's toothpaste. This reaction is just the catalyzed decomposition of hydrogen peroxide into water and oxygen gas. Granted, the demonstration also usually adds some dish soap to make it super foamy. But moving on, single displacement reactions are where things start getting strategic. A plus BC yields AC plus B. One part transfers from one compound to another. Simple enough in concept, but the key point is that this swap isn't random. A more reactive species will displace a less reactive one from a compound in solution. Oftentimes this is done with metals. For example, zinc will displace copper from copper sulfate, producing zinc sulfate and solid copper metal. If you were to try the reverse, copper in a solution of zinc sulfate, nothing happens without putting in a lot of energy. This is also the underlying logic of metal extraction. We use more reactive substances to displace desired metals from their natural ores. Now, double displacement reactions take the swap idea further. Both species exchange partners simultaneously. AB plus CD yields AD plus CB. These almost always happen in solution, and they almost always have some sort of visual indication, typically through the formation of a precipitate or a gas forming. Lead nitrate and potassium iodide is the classic visual example. 2 completely colorless solutions. You combine them and immediately an intense vivid yellow solid, lead iodide, crashes out of the solution. The reaction announces itself loudly. It's hard to miss. There's also an important subcategory here: acid-base neutralization. When an acid meets a base, they perform a double displacement and reliably produce water and a salt. Hydrochloric acid plus sodium hydroxide gives you water and sodium chloride. Clean, predictable, every single time. But baking soda and vinegar, sodium bicarbonate and acetic acid, is a more interesting example. Following double displacement rules, we'd expect sodium acetate and carbonic acid, H2CO3, which is not water. So we just broke our own rule. Well, no. Carbonic acid is unstable in aqueous solution. The moment it forms, it immediately decomposes into water and carbon dioxide gas. That's the fizz you see in the reaction. The overall reaction does give us water and a salt. It just needs an unannounced decomposition step to get there. Combustion rounds out the 5. A hydrocarbon plus oxygen yields carbon dioxide and water. Propane, gasoline, ethanol, the template is the same. The fuel changes, and there might be some additional products based on that fuel, but the logic doesn't. One important distinction: complete combustion requires sufficient oxygen. When oxygen is limited, you get incomplete combustion, and instead of carbon dioxide, you get carbon monoxide, one fewer oxygen atom. So those are the 5 types. But here's something worth sitting in. Almost all of them, all but double displacement, actually fall under a much larger umbrella. And understanding that umbrella changes how you look at the chemical reaction. That umbrella is called redox, short for oxidation reduction. To understand it, we need to talk about the thing that most chemistry is actually about: electrons. At the most fundamental level, a chemical reaction is a story about electrons, which atoms are holding them, which are releasing them, and what happens when they change hands. That is the underlying plot of most chemistry distilled into one sentence. But what's reduction and what's oxidation? Well, reduction is the gain of electrons and oxidation is the loss of electrons. I know of 2 mnemonics that help me remember this. Leo says grr, loss of electrons is oxidation, gain of electrons is reduction, or oil rig, oxidation is loss, reduction is gain. Pick whichever one actually sticks. The terms come from how an atom's oxidation state changes during a reaction, and the oxidation state is a number assigned to each atom that tracks how many electrons it has relative to its neutral form. Pure metallic iron has an oxidation state of 0. In iron 2 compounds, it's +2, 2 electrons gone. In iron 3, it's +3. When you add electrons back, you bring that number down. You reduce it, hence reduction. In a redox reaction, one species loses electrons and another gains them. The species that loses electrons is the reducing agent. It donates electrons to the other. The species that gains electrons is the oxidizing agent. It accepts them. The oxidizing agent gets reduced. The reducing agent gets oxidized. Those names describe what each does to the other, not to itself. It takes a bit to really set in, but it does click if you keep at it. Once you have this framework, you start seeing redox reactions everywhere. Rusting iron is redox. Iron atoms lose electrons to oxygen. Iron is oxidized, oxygen is reduced, producing iron oxide. Water makes iron rust faster by making it easier to move those electrons from the iron atoms to the oxygen. Combustion is redox. The fuel is oxidized and the oxygen is reduced. Fire is a rapid exothermic redox reaction happening in real time. Photosynthesis is redox. Carbon dioxide is reduced to glucose and water is oxidized and gives up electrons. A leaf is running a redox reaction powered by sunlight. That salad you're eating is solar energy stored in the form of reduced carbon compounds. Your phone battery is redox. Lithium ions migrate between electrodes as electrons flow through the circuit. Charging forces the reaction to run backwards. Discharging lets it run forwards. Your phone's screen is powered by a stream of electrons being handed off through a controlled redox reaction. Now, there's one more concept worth introducing before we move into the next section, because it bridges nicely into what comes next. When reactants are about to react, they briefly come together into what's known as a transition state. It's a temporary, unstable configuration. Chemical bonds are partially broken, new bonds are partially formed. The transition state exists for a vanishingly small moment, and then collapses, either back into the starting reactants or forward into the products. It's the top of the hill, and that hill has a name. Most people carry an assumption without realizing it. Mix reactants, they convert completely to products, reaction ends, done. But for most reactions, that's simply not how it works. The concept we need is equilibrium, and to understand it, we start somewhere familiar. You've experienced thermal equilibrium. A hot cup of coffee left on a desk stops cooling when it reaches room temperature. A balance between heat gained and heat lost. Or mechanical equilibrium. An object with no net force acting on it and stays exactly where it is. Equilibrium broadly means opposing processes have cancelled each other out. Chemical equilibrium applies that same logic to a reaction. As reactants form products, those products accumulate, and as they accumulate, they begin encountering each other, and some of them react backwards, reforming the original reactants. Eventually, the rate of the forward reaction and the rate of the reverse reaction become equal. The system is still reacting constantly in both directions simultaneously, but the concentrations of reactants and products stop changing, because they're being produced and consumed at the same rate. Not a stopped reaction, a balanced one. The position of that balance is captured by a number called the equilibrium constant. A large constant means equilibrium sits far to the right, mostly products. A small constant means it sits to the left, mostly reactants. The equilibrium constant tells you at a given temperature where a reaction wants to end up, and knowing what a reaction wants to do is enormously useful. It tells you whether a process is even feasible before you've spent any resources running it. And here's the powerful part of equilibrium. You can push that balance. This is a concept called Le Chatelier's principle. If you stress a system at equilibrium, it shifts to relieve that stress. Add more reactants and the equilibrium shifts right to consume them. Remove products as they form and the system perpetually compensates by producing more. For a lot of industrial chemistry, the discipline is manipulating equilibrium to maximize products. Pressure matters for gas phase reactions. Increase the pressure and the equilibrium shifts towards whichever side has fewer particles of gas, because that reduces volume and relieves the stress. Now, temperature is the most counterintuitive lever. For exothermic reactions, those that release heat, raising the temperature pushes the equilibrium back towards the reactants. You're essentially adding more of the reaction's own product, so the system compensates by reversing. For endothermic reactions, those that absorb heat, raising temperature drives it forward. You need to know which type you're working with before you decide what to do with heat. But equilibrium only tells us where a reaction ends up. It says nothing about how fast it gets there. That's what kinetics looks at, and kinetics starts with that hill I mentioned earlier, and that hill is what we call the activation energy. Even if a reaction is favorable, if the products are more stable than the reactants, the molecules still have to reach that transition state to get there. They have to crest over that hill. The minimum energy to do that is the activation energy, the difference in energy between the reactants and the transition state. And you can visualize this using a reaction coordinate diagram. Energy on the vertical axis, reaction progress on the horizontal. Reactants start at one energy level, climb to a peak, the transition state, then drop down to the products. If the products sit lower than the reactants, the reaction is exothermic. If they sit higher, it's endothermic. Now, for molecules to actually react, two conditions have to be met simultaneously. They need to collide with sufficient energy to reach the transition state, and they need to collide with the correct orientation. Specific atoms or bonds need to be geometrically aligned for new bonds to form. An energetic collision at the wrong angle accomplishes nothing. A perfectly oriented collision without enough energy also accomplishes nothing. Both conditions at the same time every single time a reaction occurs. This is why paper doesn't combust at room temperature. Thermodynamically, the combustion of paper is enormously favorable. The products are more stable, but the activation energy barrier prevents it without an ignition source. The match provides that initial energy. After that, the heat released by the combustion sustains enough collisions to keep the reaction going. Temperature is probably the most direct way to change a reaction's kinetics. Raise the temperature and you increase the average kinetic energy of every molecule in the system. More collisions clear the energy thresholds per unit of time, the rate climbs. This is why refrigeration slows food spoilage. You're dramatically slowing the rate at which biochemical reactions cause decay. The reactions are still happening, just much, much more slowly. And then there are catalysts. A catalyst provides an alternate pathway for the reaction, one with a lower activation energy. Reduce the height of the hill and more collisions can clear it. The reaction gets faster. Your body's enzymes are actually a type of catalyst. Each enzyme is a precisely folded protein with an active site, a little pocket shaped to bind to one type of molecule. When that type of molecule docks into the active site, it's held in the right orientation for a reaction. The activation energy drops, the reaction proceeds, and the product is released. The catalytic converter in your car does basically the same thing. Platinum and palladium lower the activation energy for converting harmful exhaust gases into less harmful products. The platinum and palladium hold the reactants in the right orientation, the reaction occurs, and the products are released. So, 3 levels. Level 1. Reactions have types: synthesis, decomposition, single displacement, double displacement, and combustion. Each describes a different pattern of how atoms rearrange, governed by the conservation of mass. Level 2. Underneath most of these types is redox, the transfer of electrons between chemical species. That electron transfer is what most chemistry is fundamentally doing. Level 3. Reactions rarely run to completion. They settle toward equilibrium, a dynamic balance between forward and reverse reactions, shiftable by changing conditions. And how fast they reach that balance is governed by kinetics, activation energy, molecular geometry, temperature, and catalysts that lower the barrier without changing the destination. The equation on the chalkboard is the summary. This is what's actually happening underneath it. And honestly, we've only scratched the surface. Step-by-step reaction mechanisms, orbital symmetry, the thermodynamic relationship between equilibrium and free energy, each of those is its own story. and maybe I'll cover those in future videos. Thanks for watching, and if you want more explanations of the chemistry at play in our lives, make sure to subscribe for more videos. And while you're at it, leave a comment down below. Which of these 3 levels surprised you the most? I do actually want to know.